So this is the second video in our installment of optimization type problems, and this is going to be a fencing problem. So if you're taking notes, I would encourage you to pause and write this down. And let's get in it. So a farmer would like to fence in an area for his goats to roam. If he was given 200 feet of fencing to make his pen, what's the maximum area possible for this pen? So we're going to look at three different cases of this problem. First case is just going to be a rectangular fence, just pretty straightforward. The second case, it's going to be a rectangular fence with fencing down the middle. So maybe he wants to separate his male and female goats so he doesn't make baby goats. That might be one possibility. And then case three, maybe he's got a river that runs through his property and knows that he doesn't need fencing on one side because there's a river that he can use as his fencing, so he can maybe maximize the possible area. So let's look at the first example, rectangular fence. We'll just draw a little rectangle here. And so we'll call these two sides the length and the width. So it's an L and a W, not the best L and a W I've ever written. And so what we want to know is we want to know what's the maximum area. So the area of a rectangle is just length times width. So what we're going to do, though, is we know that the farmer has 200 feet of fence possible for this entire fenced-in area. So we're going to use all 200 feet of this fence. So what we're going to do is we're going to come up with a second equation, and it's going to be 200 equals all the sides added together. And since we have two lengths and two widths, it's going to be 2 length plus 2W. So what we have here is we've got two equations and two unknowns. The two unknowns are length and width. And what we can do is we can solve the second equation for one of those. Oh man, I messed up here. I think I said length, but I wrote width on accident. We can solve the second one for one of the two variables and then plug it in, substitute it in for the other variable. I'll show you what I mean here. So let's solve this one for W. What I'm going to do is I'm going to subtract 2L on both sides. And I get 200 minus 2L equals 2W. And then if I want to get W all by itself, I'm going to divide by 2. And I'll give myself a little bit more room here. I end up with W equals 200 minus 2L all over 2. You could simplify that to 100 minus L equals W if you want. They're the same thing. One's just simplified down a little bit. And so what we're going to do is we're going to go back because we want to figure out what's the maximum area. And since we're trying to figure out the maximum area, we're going to plug this area formula into Desmos. But I'm not going to put L into that formula. I am going to, oh shoot, I messed that up already. I'm not going to put W into that formula. I'm going to plug 100 minus L in for W. So what I'm going to put into Desmos, if I scroll down a little bit here, is I'm going to do area equals length times width, but the width is 100 minus the length. So we're going to type that into Desmos. Let's head over to Desmos. So it's going to be length times, and what I'm going to do is use X instead of L. Desmos prefers us to use X. And then 100 minus X. And so it's going to graph this for me, and I want to find the maximum area, so I'm looking for a maximum here. Let's see. Come on. Okay, there we go. There we go. There's our maximum. So our maximum is when X equals 50, Y is going to be 2,500. So let's think about this equation for a second. The Y represents the area, and the X represents the length. And so when the length is 50, the maximum area is 2,500. So in this first example, when the length is 50, the maximum area is 2,500. So there's a couple different ways you could figure out the width here. We could type in to, whoops, I want to grab the eraser here. We'll bring that W back and use that. So it's length times width. So you could do the area equals the length times the width. And since the area is 2,500, we know the area, we know the length. We could solve that equation. We could also use the fact that there's 200 feet of fence. I didn't mean to write a 2. I meant to write a 5 there for 50. Let's try that again. The length is 50, and since we have 50 on top, 50 on bottom, that's 100, so we have 100 left over to get to 200. That means the width is going to be 50 and 50 as well, because we needed to add up to 200. So if we were asked to figure out what's the maximum area and then what are the length and width, the length and width would be 50. And so this should make a little bit of sense. If you took like a geometry course, you would understand that the optimal area of any rectangle would be a square. Okay, well, the second example is pretty similar. We're going to have a rectangular fence with fencing down the middle. So what this is going to look like is it's going to be a rectangle, but then we're also going to put fence down. So if there's fencing down the middle, that means we're going to add more fencing. So it's not going to be quite so simple. We're going to have, I'm going to use different letters here just so I'm not confusing us. So let's call each side X. So I'm going to use X here, 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 and here. And then we're going to have Y for that height. And so if we have this type of setup, we're going to have more segments of fencing. And so we're going to have, in this case, we're going to have 4 X's and 3 Y's, and that's going to equal 200. And that's going to be because we have 200 feet of fence. We're going to add up all of the different segments of fence. This is going to be our area, or our fence formula. Fence formula. But we want to maximize the area. And so the area is going to be length times width. And so, or, base times height of this rectangle. So the base of this is actually the 2 x's put together. It's going to be 2x times the height of this rectangle, which is y. So very similar to the previous problem, we're going to solve for one of the variables, and then we're going to plug it in because we want to find the maximum area. So if we want to find the maximum area, we need to plug that into Desmos to figure out the maximum area. But we can't plug both variables in. We're going to solve for one of them. And so let's do that. Let's take this first equation we came up with, and we're going to solve it for, let's solve it for y this time. So we've got 4x plus 3y equals 200. So I want to get y by itself. I'm going to subtract 4x. We get 3y equals 200 minus 4x. And I'm going to divide both sides by 3. And I get y equals 200 minus 4x divided by 3. And so what I'm going to do is I'm going to plug this stuff in for y into the area formula. And so I can head over to Desmos and do that right now. So 2x times 200 minus 4x over 3. Let's get rid of this other one. 2x times 200 minus 4x. And then I should probably, I should have been smart about this. 200 minus 4x divided by 3. There we go. All right, and so we've got ourselves a parabola. We've got a maximum here, and this time the maximum is when x is 25. The maximum area is 1,666 and 2/3. And so the maximum area goes down because we have to add that fencing in the middle. The maximum area with that other one was 2,500. Here it's only 1,666. And so if we go back to our picture, where are we? There we are. We know that our x is going to be 25, and so we could fill that in on our picture. Let me grab something. So we'd have 25 here, 25 here, 25 up there, and 25 up there. And so the total width of this rectangle, let's see, I'm kind of running out of room here. I can just extend the page down here. The width is going to be 50. If you're not sure where I'm getting 50, let's head back up to the picture. The width is, having some technical difficulties here. There we go. The width is the 25 plus the 25. It's that whole distance. And then the length is going to be the y value. Well, we know that there's 100 feet of fence with the 25, 25, 25, and 25. 25 times 4. 25 times 4 is 100. So that means I've got 100 left over for the other three segments. So if I take 100 divided by 3, y is going to be 33 1/3. That's just 100 divided by 3. And so the length of this is going to be 33 1/3. The maximum area, max area, we said was 1666.6 repeating, or in 2/3. All right, so then the third and final iteration of this would be, what if this farmer has a river on one side? And so I'm going to draw a quick river. There's our river. Well, let's make it a stream here. There we go. There's water down that river. And so then the fencing is just going to be 3 pieces of fence, like that. We'll call this, again, we'll call it x. Well, I'll be consistent with what I did last time. So the y was the vertical piece, so let's call that y. It doesn't really matter. But just for consistency, we call it x and y. And so we know that if we add these 3 segments up, x plus 2y, that's going to give us 200 feet of fence. And the area of this is going to be x times y. Remember, we're trying to maximize the area, so that's what we're going to plug into decimal. So a lot of times people get confused, and what do I plug into the calculator? It's always when it says, what are you trying to maximize or minimize? That's what you're going to be plugging in. So you're going to be substituting things into that formula. So the first formula that we came up with, this x plus 2y equals 200, that one is going to be pretty easy to solve for x. I'll rewrite it down here. X plus 2y equals 200. I'm just going to subtract 2y from both sides. 2y, there we go. Best penmanship of the year here. And so we get x equals 200 minus 2y. And so what I'm going to do is replace x with 200 minus 2y. So that's going to go in for x into the area formula. So in decimals, I'm going to type in 200 minus 2y, and then times y. So I haven't talked about domain yet. This would be maybe a good time to talk about domain. Domain is usually what can x be. Now, I arbitrarily chose x and y, so let's talk about what can x be and what can y be. Well, the biggest thing that x can be, so x can't be 500, because you can't have a piece of fencing that's 500 here for x when you only have 200 feet of fence. So x could be everything up until 200, right? You'd have this really long, skinny rectangle. It would be kind of silly because goats couldn't fit in there. But if you got like 199 feet for x, then you'd have a half a foot for y and y. So x would be the domain for, what possible x values are anything from 0 to 200. For y, it would be anything from 0 to 100 because you have two of those, and 100 plus 100 is 200. So the y values, if you're talking about the domain of y, which is kind of weird to say because usually domain means x, but it doesn't have to. But the domain of the y situation here would be that y, the maximum y through e is 100. So that might come up. I just wanted to address that while we're on it. So back to Desmos. We'll type this in, 200 minus 2y, and then times y. So 200 minus 2y. And I'm going to use x, just Desmos works better with x. And then times x. And look at this, we actually get a much bigger area. When x is 50, this is confusing. This is really representing y, right? Because we plugged in, we use y. I probably should have been a little wiser about this. But anyway, when our y value is 50, the maximum area is going to be 5,000. So it's much bigger than using it or doing 4 sides of fencing. That river really maximizes the area. And so when y is 50, the area is going to be 5,000. Remember that y value in our formula, like when we're typing in Desmos, that represents the area. So the maximum area is 5,000 when y is 50. So y would be 50 and 50. That means we used 100 feet of fence there, so we have 100 left over for x. And the maximum area is going to be 5,000. I don't need to write that down. You can write that down if you want to. So anyway, this is just another type of optimization type problem in 3 different, very different situations, but all very similar. So this is more of the optimization fence type problem.